Good afternoon, good morning, good evening, dear friends, dear colleagues. Welcome to our seminar on optimization. Today, our speaker will be a young colleague from the University of Minnesota, Ying Cui. She received her PhD in mathematics in Singapore, if I'm not wrong, namely in 2016, under the supervision of Defeng Sun and Chen Leng. And she spent another year in Singapore in the group of Kim Chuan To, and moved in July 2017 to the University of Southern California in the research group of Zhongxi Pang. And she spent more than 2 years in California, and in the beginning of 2020, Ying moved to the University of Minnesota on the position of assistant professor. She is working on many interesting topics of optimization that I would like to emphasize, in particular stochastic programming, and has a number of great publications in the top-ranked journals. And last but not least, I'd like to mention a recent book, a new monograph she wrote together with Zhong Xi on non-convex, non-differentiable optimization. So, Ying, thank you for accepting our invitation. You have 45 minutes for your talk. The floor is yours.
All right, thank you very much, Radu, for having me here today. And it is really my great pleasure to share with you my recent work on the non-convex stochastic programs. So this is based on the joint work with my first year PhD student, Han-Yang Li at the Minnesota. And I would also like to acknowledge 3 people, although they are not really involved in this work. So Jin Liu, who is currently at Tsinghua University, and my postdoc advisor, Jungxi Pan, who is here, and also Professor Severin Sun from the University of Southern California. So the reason I want to acknowledge them is because this current work is really based on our previous joint works on the non-convex stochastic programs. And also they are the people that really brought me to this field of the stochastic programs. So thank you. Okay, so let me begin my talk with a very brief introduction about two-stage stochastic programs. So this is a very, very classical paradigm for the sequential decision-making under uncertainty. And basically we have 2 sets of decisions. So one set of the decision X we need to make before we really realize we have the exact information of the data. And so those part of the decision, we call it the stage 1 decision. Okay, so which is here at the very beginning, we make this set of decisions. And then we can observe some data, or there is some resolution of uncertainty so that we can have a recourse action based on the realization of the uncertain data. And then this part of the decision, we call it the stage 2 decision 1. And actually, there is quite a long history of the stochastic programs that really dates back to 1955. And there are also a lot of monographs that give very nice introduction and foundations of the theory, the algorithms, and the applications of the stochastic programs. Okay, so here, let me just give a very simple and typical example of the 2-stage stochastic programs, which arise from the power system planning. So in such kind of power system planning, usually the demand of the electricity from the consumers, they are not known exactly when we want to determine the capacity of the power plant and also the unit price of the electricity. And also if the system, within the system, there are some renewable energies, and then the production, the amount of the production of the electricity from such kind of renewable energy is also uncertain. But after we observe this kind of uncertainty in practice, then we can make a recourse decision or a stage 2 decision that to allocate the production of the power plant to different locations. So these are the stage 1 and the stage 2 problems. Okay, here are the specific formulation. And as a very simple example, I want to start from the two-stage linear programs. So by linear programs, it basically says that everything here in this problem is linear. Okay, so here say zero transpose x is the first stage objective function, which is linear in the first stage decision x. And here is the recourse function, which is actually the value function of parametric linear programs. And one thing I want to emphasize here is that in the classical paradigm of the two-stage linear programs, so actually x, the first stage decision, only appears in the constraint of the second stage problems. Okay, and the objective function, although it is linear in y, but it has nothing to do with the first stage decision x. Okay, so that is the two-stage linear program, which has received a lot of studies. Okay, so such kind of problem, actually, if we know, so because there are some uncertainty here, which I use the random variable omega, or it can be a random vector or random matrix. So, but I generally denote it as omega. But if we have some realizations of this omega, or if you just imagine that these realizations, it can be the historical data, or it can be just the sample average approximation of the general distribution of omega. Okay, but anyway, if we are given a set of the realizations of omega, actually this kind of two-stage linear programs has a deterministic equivalent that is consist of the first stage variable x and also a set of the second stage variables y. And here notice that actually so it depends on how many realizations you have, then how many copies of the second stage variables you will have. And the reason is really because our second stage, the recourse decision, will depend on the particular realization of omega. Okay, so which means whenever you have one omega, you will have one set of y. Okay, so basically this problem here, the deterministic equivalent problem, is a linear program. And the only thing that may make this problem special is that the dimension of this problem may be large. And the reason is simply because if you have very large S, then this problem size will be linearly dependent on S. Okay, that is the reason why in the two-stage stochastic programming literature, a lot of attention was paid on the decomposition methods. And by decomposition, it means that, okay, we only want to solve relatively small size of subproblems for each step instead of solving the whole deterministic equivalent problem, although it is linear.
We have a question.
Sure, of course.
Yes, Manuel Bomb.
Dr. Cui, for interrupting, just for my understanding, so you're assuming equidistribution here, right? All scenarios are equally probable.
Yeah, so for now, let's assume if we only have discrete distribution, or this, you can also view this as the sample average approximation of the general continuous distribution. But I mean, even if we are
this is the point, even if everything is nice and
exactly,
then it becomes difficult. Thank you.
Yeah, exactly. And I will also talk about if this is just a general continuous distribution and how can we do it properly with the sampling. But for now, I mean, even if this is a we have only finite number of scenarios, then the resulting problem, the deterministic equivalent problem, can have potentially very large scale. And that comes the need of the decomposition method. And actually this, although it is a linear program here, but this is not a generic linear program. It has a very special, whenever we have two-stage stochastic program, the resulting problem, the deterministic equivalent problem, will have a very, very special structure on the constraint set. And the reason is really because we have single X and we have multiple copies of Y. And all these copies of Y, they are decomposable in the constraint, meaning that For example, if you have two realizations and you have y1 and y2, but the y1 and y2 will not appear simultaneously in one constraint. So that, or in other words, actually the constraint of the two-stage linear programs have a block angular structure. And there are 2 points of views to view this block angular constraint. So one point is from the primal angle that, okay, we have single x, but we have different y's, but all those y's, they are in the block diagonal structure. And this kind of block angular structure enables the bundles decomposition. And also there are a lot of variants of this kind of bundles decomposition, but they are really based on this block angular structure of the constraints. And of course, you can have a dual view of this kind of block angular constraint by simply copy the first stage decision variable. So because we want to have a unified x among different scenarios, then maybe for each scenario, then we can give a copy of x and just to make sure that out of this x, they are the same. So which is actually called the non-anticipativity constraint in the two-stage stochastic programs. And based on this kind of, adding this kind of non-anticipativity constraint, we can also do the dual decomposition method based on the Lagrangian relaxation. And there are many methods to do the Lagrangian relaxation in order to update the multipliers. For example, you can use the separating method. You can also use the cutting plane method. And if you are willing to add a proximal term, and you can use the augmented Lagrangian method, or we call it the progressive hedging method, which is actually a variant of the alternating direction method of the multipliers for solving such kind of specialized two-stage stochastic programs. Okay, so one thing I want to mention is that, okay, why the bundles decomposition, which is a very, or perhaps the most classical decomposition method for the two-stage stochastic programs work. And actually, if you look at the details of the algorithm, then the key factor to make this algorithm work is because if you look at the value function, or we call it the recourse function here, which is actually the optimal value of a parametric linear program, then this function is convex and it is also piecewise affine, which is actually very simple to get from the basic perturbation analysis of the linear programs. And because this function is convex and piecewise affine, then we can always derive the supporting hyperplane of this value function so that whenever we get an optimal solution of the dual problem, then we can add one cut to get a linear lower approximation of the recourse function. And because this function has only finite many pieces, then you can gradually add those pieces to really give more and more accurate description of the recourse function. And because whenever you are given X to solve this problem, you only need to consider one scenario each time and solve the corresponding Y. So that is the reason why this algorithm is decomposable over different scenarios. Okay, then those are the algorithms in the existing literature. And what we are really interested in now is, okay, why X only appears in a constraint? So how about the case that X even appear in the objective function of the two-stage problem? So which means when you make a recourse decision, then the objective, or sometimes in the operations research, this really represents the cost function. So this cost, it can happen that this also depends on your first stage decision. And especially this kind of phenomenon can appear if your probability distribution here, P, depends on X, so which is called the decision-dependent uncertainty. Okay, we have a previous paper published in Science Optimization that gives some examples that why this kind of problems are interesting. Or in other words, why X can, instead of just appearing in the constraint, why it can also appear in the objective function. And here I just make it very simple that okay, x, although it appears in the objective function, but it only appears in a linear way. Or in other words, the objective function is bilinear in terms of x and y. However, even for such simple modification of the classical two-stage linear programs, then the resulting recourse function here, phi, as the value function of this optimization problem, it is no longer nice. Okay, so instead of being a convex piecewise affine function, then such kind of function can become non-convex. So here I just draw two simple figures to illustrate what can happen in the one-dimensional space and also in the two-dimensional space. And you can easily find that actually this value function, it becomes quite non-convex, and it works in a very nonlinear way. And also there are some non-smooth point here and maybe here. Okay, so which means with a simple modification of x of the second stage problem, then even it is in a linear way, but the resulting two-stage stochastic program can become quite complicated. And which means that, okay, if you have such kind of non-convexity for the value function, then the Bender's decomposition, this kind of method, can no longer work. Because of the non-convexity, then you cannot get a simple linear lower approximation at each point. For example, you can imagine if you are at this point, then you can never use a linear function to get a lower bound of the original objective value function. And that really brings the difficulty to design the decomposition methods for solving such kind of stochastic programs. And actually, in our work, we consider a more general situation that we allow both the objective function and the constraint in the second stage to be dependent on x. And they can be quite general in the sense that we assume the objective function, which is strongly dependent on x and y, that they are concave convex, meaning that if you fix y, then it will become the function f must be convex, must be concave in x, and if you fix x, it must be convex in y. So in particular, this covers the bilinear case, which is actually linear. Okay, and that is also the reason that we don't want to assume this f is jointly convex, because if we assume f is jointly convex, then it cannot cover the bilinear case, which is actually not jointly convex in x and y. And for the constraint function, we assume it is jointly convex in x and y. And we make such kind of assumption because we still want to assume that if we are given x, the first stage decision, then this optimization problems in terms of y is relatively nice, in the sense that it is still a convex problem in y. And we also allow the function f and g to be non-smooth. So there are no smoothness requirements for this problem. And what we are trying to answer in this work is, okay, given such kind of two-stage stochastic programs, how to generalize the Bender's decomposition so that we can still get a decomposition algorithm for solving such kind of problems. Okay, what is the difficulty for solving this problem, or to design the decomposition methods for solving such kind of problem? Is actually in the properties of the recourse function. So as I mentioned, even if for a bilinear case, even if the second stage objective function is bilinear, then the recourse function in terms of x here, it can behave quite badly. Okay, not to mention this general situation. And there is a fundamental reason that this problem is difficult. That is actually because the recourse function can easily fail to be Clark regular. Okay, so what is Clark regular? Clark regular is it can be defined for a discontinuous function, but here just for simplicity, we assume we have a local ellipsis continuous function. Then we see this function is Clark regular if it's your one-sided directional derivative coincide with the Clark directional derivative. And of course, there are a lot of ways in the literature to define the Clark regularity, but here is just one, and all of them are equivalent. So here I just gave one simple condition. Okay, and there are a lot of functions that satisfy this clock regularity, and in particular, our convex functions and even our weakly convex functions, they are clock regular, and our smooth functions, they are always clock regular, and also some composition of the convex, the composition of the smooth and the convex and smooth functions, they are also clock regular. Okay, so although the family of clock regular functions are very broad, but unfortunately, it cannot cover everything that we are interested in. So geometrically speaking, so what is the meaning of the clock regularity, or when will it happen that the function is not clock regular? So actually it means that for a continuous function, when will it fail to be clock regular? It means that, okay, in this function, then there is a downward cusp. So it is okay that this function is non-smooth. For example, you can have an upward cusp, like the absolute value function at 0, but you cannot have a downward one. Okay, and if you want to have a downward structure, then it can only be a smooth structure, like the minus x squared function. Okay, so whenever you have a downward cusp, then the function will not be clock regular at this particular point. And of course, we can also define the clock regularity of a set, and when the set fails to be clock regular, it means that, okay, for this set, there are some inward counter. So again, it is okay to have outward counter like a polyhedral set, but it is not okay to have an inward counter. So whenever you have an inward counter, then the set is not clock regular. Okay, that is the geometric intuition of the clock regularity. But it goes back to our recourse function, and even in the bilinear case, then you can see this function here at this particular point, actually you have a downward cusp. So which means that such kind of recourse function easily fails to be clock regular. And also when in a two-dimensional case, you can imagine here it may not be clock regular. Okay, so then how can we solve this problem? How can we design the decomposition method to solve such problems? So if actually for the bilinear case, this function is not that bad in the sense that actually this is just means that we have a linear program, but in Y, but both the objective function and the constraint are perturbed. And we consider the sensitivity analysis for such kind of value functions. And it can be proved that this function is always a piecewise linear quadratic function, although it may not be convex. So, and also it can be proved that theoretically, this is a difference of convex function. So the difference of convexity, this property is important because if we really have a difference of convex functions, then we can always linearize the second convex function so that we can get an upper bound of the original function. And that is the building block of the difference of convex algorithms. However, the trouble is that although theoretically you can get the difference of convex decomposition of this recourse function, but its DC decomposition is not very computational friendly in the sense that actually we need to compute, at least as far as I know, we need to compute all the extreme points of these polyhedral sets so that you can get its DC decomposition. And that is really something that we want to avoid in the computation. So which means, okay, theoretically this function is nice, but it may not be that, this property may not be that useful when we want to design the decomposition method. So what can we do? And as I mentioned, actually this problem is not that bad because this is really just the sensitivity analysis of linear programs. So if we fix, so because the difficulty for this problem is because the objective function and constraint, they are simultaneously perturbed by X. But if we fix one of them, for example, if we fix the objective function, then this is just the perturbation of the constraint of a linear program, now which we easily know it is convex piecewise affine. And reversely, if we fix the X in the constraint and only perturb the objective function, then this is a concave function because it is the minimum of the concave functions, and it is also concave piecewise affine. Okay, in other words, if we only consider one perturbation, no matter it is perturbing the objective function in the constraint or in the objective function, this problem is nice. But The trouble is here we want to consider joint perturbations that X appears in both parts. Okay, so what can we do? But one thing I want to mention is that actually there are extensive variational analysis for such kind of perturbations when both the objective function and the constraint are parametrized. And you can find them in this monograph on the perturbation analysis. Okay, what can we do? We want to resolve this problem when it is jointly perturbed by the same parameter. Okay, so as I mentioned, because if we fix one of them, then it is nice. Then how about we lift this function in a higher dimensional space? That in the sense that we want to split the perturbations or the rows of the parameters in this problem. So the original problem or the original function, this function phi of x is just in the x space. But here, how about we introduce a copy? If we split the function into two parts, where the objective function is determined by z and the constraint is determined by x, then actually we know that this is a convex concave function in the sense that if you fix z, then this function is convex. And if you fix x, this function is concave. Okay, so in other words, it behaves nicely in a higher dimensional space. And, oh, sorry. Okay, then, but we want to go back to the original space because we want to enforce the consensus of z and x. They are not allowed to take different values. Okay, so going back to the original space, actually this is a concept that we introduced in our side of the paper that we call such function in the x space only implicitly convex concave. So why we say it is implicitly convex concave? Because here we only have a single parameter that is, simultaneously affect the objective function and the constraint. So we don't have an explicit convex concave structure. But nevertheless, if we split the variables, then we have this kind of decomposition or this kind of relatively nice structure. Okay, and actually in our monograph, which we just published with Junxi Pan, we can show that this kind of implicitly convex concave property holds for a very broad class of optimal value functions. Okay, so by definition, what is implicitly convex concave? It just means that, okay, if you give me a function, then if this function can be associated with a bivariate function that is convex concave, and those two parameters, when those two parameters coincide, it reduces to the original function, then we see the function is implicitly convex concave. And just as a remark, so another reason why we name it implicitly convex concave, because the difference of convex functions is actually explicitly convex concave in the sense that we can always associate a difference of convex function with a bivariate function by changing the second variable x to z. So then you can easily see that when x and z are the same, this reduced to the original function, and also the associated bivariate function is convex in x and concave in z. Okay, but just for our problem, as we mentioned, although we know it is difference of convex, but we don't know it's explicit decomposition. So that is the reason we call it implicit convex concave. And here is just a figure to further illustrate this idea. So imagine if our original recourse function, the decision variable x, is just a univariate variable. So we have this kind of recourse function, which is very bad. It is non-convex, and we don't have a very good understanding of this function. But we can lift this function in a two-dimensional space. And only if x and z are the same, this reduced to the original function. When x and z, they are not the same, of course, they cannot be the same as our original function in the R space. Okay, the reason why we consider to lift the univariate function to a bivariate function is because this two-dimensional function is concave. If you fix z, if you fix x, then this is a concave function. And if you fix Z, this is a convex function. So that is the concave convex structure if you fix one of the coordinates. Okay, but why do we need this kind of implicit convexity concavity in the decomposition algorithm? And here's the reason. Okay, so we can, it is well known that we can define the Moreau envelope of a function. And even if it is, although most of the time we consider this kind of Moreau envelope in the convex case, but of course we can also define it in the non-convex case, and especially if it is prox regular. And it is also a very nice property that the Moreau envelope can always be decomposed into the difference of convex form, even if F is not convex. And this is just by some simple computations, and it is known in the literature. Okay, so this part is convex in X because it is the soup of convex functions in terms of X. However, the difficulty is that if F is not convex, especially if F is not Clark regular, means that it is not prox regular, this function in terms of Y, it may not be computable. Because for example, if F is convex, then this is always strongly concave in Y, it is always computable. But if it is not convex, for example, it is the negative absolute value, it is the absolute value function, negative absolute value function, then this, you may not be able to get a solution here. And that is really the reason why when F is not Clark regular, this problem is difficult. So meaning that, okay, although in principle, the Moreau envelope can always provide us a difference of convex decomposition, but it may not be computed, the second part may not be computable, which means it may not be very useful in designing the algorithms. Okay, and unfortunately, in our problem, it is not the second part is not computable. And the reason is just because it is not Clark regular. So you may not even have the existence of the solution. Okay, so what is the resolution? Actually, we changed the Moreau envelope a little bit. So because the trouble comes from the non-convexity of the value function, then how about we only consider the nice part, the Moreau envelope of the nice part. And the reason why we need this kind of discussion is because in order to generalize the Bender's decomposition, what we are trying to do is to get a good surrogation of the recourse function whenever you give me an X. Okay, so recall that we said that the recourse function is implicitly convex concave, means that, okay, we associate that recourse function with a bivariate function. And this function is convex in X and concave in Z. Okay, so when we define the Moreau envelope, actually we only consider the part in terms of X, which means we only consider the part that is convex. So that we want to make sure that after we get the decomposition, it is decomposable. No, it is computable. And here we draw the figure. Okay, so the blue line is still refers to the original recourse function, and then the red part is the partial Moreau envelope. And it is easy to see that this is always a lower bound of the original problem, and the gap diminish when gamma goes to 0. So it will get closer and closer to the original function when gamma is smaller and smaller. Oh, sorry, I forgot to mention here means that for different gammas. And gamma here is relatively large, but on the right, the gamma is relatively small. Okay, so the nice thing is that if we modify the Moreau envelope and define it in this way, then when we get the difference of convex decomposition, the second part is always computable. And the reason is because, okay, let's look at the second problem here. So if you give me Z, then this function, because the phi bar function is convex in X, then this inner part in terms of X is always strongly concave. So that whenever I give you Z, you can compute the objective value of this function. Or in other words, this G gamma Z, the entire function is computable. And also its subgradient is computable based on the Danskin theorem. Okay, so which means, okay, nicely we can get a surrogation of the partial Moreau envelope by simply linearizing the second part. And because its subgradient is computable, then we can always use the subgradient equality to get a lower bound of the second convex function, so that putting them together, it gave us a convex upper bound. And what is even better for this problem is because we have a strongly convex term here, so the upper bound we get is strongly convex. Okay, so which means, okay, although we are not able to design a upper surrogation of the original blue function, but we can sacrifice something to get an upper bound of the partial Moreau envelope, which is the orange curve here. And as I mentioned, if gamma becomes smaller and smaller, then this red line becomes closer and closer to the original function, so that the orange curve will become more and more like a convex upper bound of the original function. Okay, so in other words, although we don't know an explicit difference of convex decomposition for the value function, but still we are able to get some inexact upper bound of the original function. And that is really the basic of the decomposition algorithm. Okay, going back to the original problem. So how to decompose it? And here again, let's just simply consider the fixed scenarios so that we have the sample average of the recourse function. And for each recourse function, we need to know what is the corresponding optimal solution for what. Okay, so this is the decomposition algorithm. So we ask them in the Bender's decomposition, we have a master problem, we have a subproblem. And for the master problem, it is simply in the dimension of the, in the X space. So only consider the first stage variable. And because we can get an estimation of the recourse function based on the previously discussed partial Moreau envelope and its decomposition. So here, this E hat gamma means we get the upper bound. So hat just means the upper bound, and E gamma means the Moreau envelope, the partial Moreau envelope. So this is the estimation, or you can see this is just an upper estimation of the recourse function at a given X. Okay, so to solve this problem, it is only in the dimension of X. And because we need to get this upper bound, then we need to solve the subproblems. And for each subproblem, it just means that you need, if I give you X, you need to solve a corresponding Y. So of course it is decomposable over the scenarios, just as the case for the Bender's decomposition. Okay, so we do it iteratively, and because we introduce this Moreau envelope, then there is a gap between the Moreau envelope and the original function. So we also need an outer loop to update this gamma to decrease the gamma to 0, so that it becomes closer and closer to the original function. So that, or in other words, you can imagine that this kind of upper bound is becoming closer and closer as the upper surrogation of the original recourse function. Okay, and we can prove that, although we need some technical conditions, but we can prove that the any accumulation point of this algorithm is a stationary point. But of course, there is a question of what is the meaning of the stationary point here, because we have a non-convex regular function. And it turns out that we can define it in the, it is a relaxed condition just as the critical point of the difference of convex algorithm. But because we have this implicitly difference of convexity, then we can define a corresponding point. But that is quite technical, so I didn't want to talk into detail about that part. And we can further get the sequential convergence of the objective value if we under some conditions on the Moreau envelope parameters. Okay, but just as a technical note, so this algorithm is not really the difference of convex algorithm, or the, you can call it the majorization minimization algorithm. And the reason why it is not, it cannot reduce to the difference of our convex algorithm is because actually our surrogation, which is the orange curve here, it is not really a convex upper bound of the original function. So it is not really a majorization, but rather it is the majorization of the Moreau envelope. But the Moreau envelope itself is only a lower bound of the original function. So you get the upper bound of the lower bound of the original function, then you cannot simply say this orange function is the upper bound of the original function. But it can also, it may not also not be a lower bound of the original function. So in other words, it is just an approximation of the original function. But because the Morrow envelope is becoming closer and closer to the original blue function when gamma goes to 0, then the orange function is like an inexact upper bound of the green function. So that is the reason why with a proper control of the inexactness, we can get the convergence of the algorithm. Okay, then comes the problem that how about a general situation that we don't have fixed scenarios or we don't have a discrete distribution of the probability measure? Then of course, just as in the general discussion of the stochastic programs, we can do the sampling. So each step, and here is actually we do the sampling in the interior. We mean in the sense that we do the sampling simultaneously when we update the parameters. So it is different from the sample average approximation where you first get a set of samples and just solve the optimization problems in terms of this set of samples. But here we are gradually adding the samples to the master problem with the progress of the algorithm. Okay, but the other part, they are the same. Just instead of the original fixed scenarios, we consider the recourse function based on the sampling here. And under some requirement on the sample size for each problem, we can still get the same convergence, but in the almost sure sense. And here is a numerical experiment. And I will say that it is still preliminary and we are still trying to wrap up this part. But we are trying to compare because our problem is just a nonlinear program, actually. If you consider some simple cases, for example, if you consider the bilinear case, then the deterministic equivalent is actually a non-convex quadratic program, which means that problem, if you consider the deterministic equivalent, then you can use the general purpose nonlinear programming solver to solve it, although it is non-convex. Okay, so we choose to compare it with natural, which is highly optimized commercial solver for the nonlinear programming. And we consider two sets of algorithms in the natural. We choose to use the interior point method to deal with the constraint, and we consider both the direct solver and the CG. And this direct and CG, it refers to how you solve the KKT system in the interior point method. Okay, so you can easily imagine that because the nitro, it can only do, it is not a decomposition method because it is a generic solver. So you need to solve the deterministic equivalent problem. Then it can easily blow up with the scaling of the scenarios. And this, the number of scenarios here we listed is about 50,000. And then under this configuration, then the number of variables is about 2 million and number of constraints is about 4 million. So for such kind of problem, so roughly speaking, we need, I think about 1 minute on average to solve it. And actually we can, what is even good is, although I didn't list it here, but I did some numerical tests that even if we have like, we continue to scale up this problem. For example, if we have 1 million number of scenarios, so that the number of constraints is actually 40 million, 40 million, then we need about 2 minutes to solve the problem. So actually it works pretty well. But if we switch to CG method of the interior point method implemented in natural, it actually also scale well, relatively well, but it is, we find that actually if you look at objective value function, although we stopped algorithms by the same criterion based on the KKT conditions, but if you look at objective value function that is given by the CG method, it is significantly worse than the objective value function computed by both our decomposition method and also the direct solver. Actually, the objective value obtained from our master, and the direct solver, they are roughly the same. So you cannot see the difference, and these two lines, they coincide. But the objective value provided by CG is actually significantly worse. And we found that actually, if we continue to make the accuracy higher, in the sense that if we allow the CG method to be more accurate, then this objective value will be close to our algorithms. But then the CG master will take a significantly long time, so that we didn't really give the a plot of the computational time here if we want to change the KKT residuals. But the main message I want to say here is that, okay, if you want to get, of course, the direct solver, if you want to direct solve the linear system in the interpolation method, then this kind of algorithm cannot stick well. Although it performs super well for the small scale, but it cannot really work well in the large scale. Okay, and if you change to the CG solver, which is actually friendly to scaling, but you will not be able to get the same quality of solutions as ours. And actually, we can find out if we continue to scale up these problems, actually the gap between our master and the CG is becoming larger and larger. Okay, so that is the numerical performance of our algorithms. Okay, so I finished my talk, and just as an advertisement, so we with Zhongxi, we finished a monograph on the more than non-convex and non-differentiable optimization, and it is now available at Sam store. Actually, just last month I received hard copy, so which means that other hard copy is also available here at this moment at Sam bookstore. And if you are interested, then maybe you can take a look at it. Okay, that's all for my talk, and thank you very much. I'm happy to take any question.
Thank you, Ying, for a very interesting talk. Thank you very much. Are there any questions? Jonathan.
Yeah, a couple things. One I'm kind of interested is, you gave this theoretical convergence result.
Mm-hmm.
If you terminate early, is there any guarantee that you'll at least be feasible for the second stage?
It may not. The reason is because here in the decomposition, actually we introduce this mirror envelope. If that gamma is not small enough, then because we do the lifting, so that actually there is a gap between the objective function x. And if you remember, when we do the lifting, actually it is x and z, they are not forced to be the same. Oh, sorry, which is,
it's too fast.
sorry, it is here. So the original objective function, the recourse function, x and z, they must be the same. Mm-hmm. And when we do the algorithm, we have a gamma, so that actually if a gamma is not small enough, then there is a gap between x and z. So that actually it means that this function may not be a very accurate estimation of the original recourse function. Right. Then there is some, but because we use the different variables, something like we use different variables in the objective and in the constraint, and that may create a gap in the feasibility. So we can only guarantee the feasibility for the z part, but if x and z, they are not consensus, then it may not be feasible. The point of a program may not be feasible. Yeah.
Because that's what I was worried about. I mean, because what a decision maker would care about is, okay, at least I'm close to a stationary point when I stop, so I have a pretty good solution I can put in practice. But if it's not feasible in the second stage, then they're not going to be happy.
Yes. In simple, I totally agree that the feasibility is really an issue here if you want to do the early stopping. But actually, we have observed, based on our numerical experiment, we have observed that, so we don't need a lot of update on gamma. Mm-hmm. And you can also imagine this gamma is like a penalty parameter on the difference between x and z. So it doesn't need to be updated a lot of time. And so which means actually you don't need to wait a long time until you see the feasibility. Usually we just update several times, like within 10 steps for this gamma.
So at a certain point, so your stopping criterion can be, feasibility plus some tolerance. And in practice, you seem to get the feasibility fairly soon.
Yeah, and if you really care more about feasibility compared with the optimality, then you can start with a relatively small gamma. Means that you just give me a very large penalty, then it easily becomes feasible. although you may pay more work, you need more work on solving the subproblems, and it may not provide a very optimal solution, but just in terms of getting feasibility, we can start with a relatively small gamma, or we decrease gamma very quickly. It can help in terms of the feasibility.
Okay, thank you.
Thank you. Sanjay?
Yes, I have a very small question. So one of your assumptions is that the second stage cost is convex concave. And I wanted to ask you, what are the problems in which this structure occurs? You know, because you had at the very beginning, you had this structure here. Oh yeah, here, exactly this. So this was one of the assumptions, right? So this is my question: is where do this type of problems actually occur that you can enjoy? Because everything hinges on this convex concavity of the function in your analysis, what I understand. You mentioned, for instance, the decision-dependent distribution. But if you have a decision-dependent distribution, you will never obtain a convex-concave structure, because the probabilities are bounded, therefore cannot be convex or concave unless they are constant. So.
No, I mean, if the probability density function here, although it depends on x, but for example, it depends linearly on x, then if you write down
probabilities are bounded. So if you have finite number of scenarios and the probabilities are, cannot depend in a convex way on x, there's no way.
Let me see. No, I mean, like if you have the.
Sorry, but sorry to interrupt, Anjay and Ying. Sorry, but X can be bounded. The ground set for the X can be a bounded set, and then the argument does not hold anymore, right? X need not be the full space.
Yeah, it would be good. So what I wanted to say, you would strengthen your work very much by showing some colorful application areas in which this type of structure occurs.
Yeah,
that's
so
what I wanted to mention.
Yeah, thank you very much for your suggestion. So maybe I can give you an example why this decision dependent can have a linear case. Is, for example, you have this represents the cost function of something, but usually if we fix this cost, so like in the Euro case, then it means the unit cost is independent of x. But if the unit cost for the second stage problem is linearly dependent on x, then this will have a linearly objective function in terms of x. So that is one case for the decision dependent uncertainty. And the uncertainty is in the cost, but it is linearly dependent on the cost. And maybe another example is actually we want to cover some interdiction problem where actually instead of the minimum of the recourse function, we want to consider a maximization problem. And the maximization problem, the objective function is independent of x, but you have a constraint in x. But then if you want to use the duality to change the maximization to the minimization problem, then this x, it can appear linearly in the objective function instead of in the constraint. So that is also another reason. So although there are extensive work on the stochastic network interdiction problem, but if we consider a general setting for the min-max problem, where the recourse function is to maximize something, then you can have this kind of dependency on x in the objective function and also in a linear way. So that is also another reason that we consider this problem. But I totally agree with you that it is very important to do some colorful applications of these problems. And yeah, I think we will do it in our work. Yeah. So thank you very much for your question.
Thank you, Ying. Manuel?
Thank you. Thank you, Dr. Cui, for your excellent presentation, very clear. I have two questions, and it is related to this slide you have, 7 or 8, it doesn't matter. So this may deviate slightly from the tradition of stochastic optimization, but we were considering recently constraints which are not stochastic, right? So they couple the X couples with the different scenarios Y's by a deterministic or a set of deterministic constraints, whereas the objective, this d omega, for instance, would be a non-convex, neither convex nor concave function jointly in X and Y. I can just post in the chat the relevant paper if you want to consult it. So, and my question would be, do you see a chance to do this Bender's decomposition in some cases I just outlined? So not extending, because you extend on the objective function, but you shrink the assumptions or narrow the assumptions on the constraint.
So for one thing, there is a very important assumption in our work, that is, if we are given X, then these problems in terms of Y is relatively easy. And here, that is the reason why we assume this kind of convexity in Y. So given this, our generalization of this Bender's decomposition relies on this assumption, because we need to still, if you are given X, we need to provide a valid solution for Y for second stage. Just this recourse is not convex in X. But am I right that in your situation, you want to consider a more general situation, that even given X, you cannot really get Y by some, simple algorithms?
Definitely not simple. Yes, it's a non-convex subproblem.
Yeah, so I would say at this moment, I don't know how to generalize the Bender's decomposition of that one, because our idea here is that we want to get a good approximation of this recourse function. And that depends on the ability to solve Y. But just how to approximate this non-convex shape in terms of X. But if we are not able to solve Y, then I'm not very sure how to generalize this algorithm. But I think one thing that is possible is to consider the generalization of the progressive hedging. That may, I'm not very sure, but I feel that may be relatively easy than this kind of Bender's decomposition to do it in a primal way.
Okay, so of course, this would follow a general paradigm of proximate solutions also in Y. It's not a closed form solution. You have an algorithmic solution to detect Y given X, and it's true, no?
Yes.
It's somehow connected to the question Jonathan Eckstein was asking, no? Because what do you have some guarantees? But in my case, in the case I outlined, there is no problem with feasibility. So it's just a guarantee, optimality guarantee, not a feasibility guarantee we are chasing. So in this sense, it could be related. So you solve approximately with some guarantee or some quality guarantee in Y, not exactly, and then proceed.
Okay, so which means you can tell some property of the computed solution for Y with respect to the true solution for Y.
Yes.
Okay. I will take a look at your paper and see what's going on there.
It is for sure a complementary view on this, and not correcting or extending, or unfortunately not extending your approach. Thank you very much.
Thank you very much.
Thank you very much. Are there other questions?
Yeah, I just want to mention, there's a very nice class of problems, which you essentially mentioned, but it's stochastic bi-level.
So,
okay. So the idea is, a leader makes a decision, then uncertainty is revealed, then a follower, then some opponent or follower or something makes another decision. So it's a quite simple class, but there's many hard, interesting problems that fall in that class.
Yeah, exactly. Especially if the I mean, if the followers problem, they have different objective, it cannot be rewritten as the min-max problem, then yeah, it means that we need to analyze the optimal solution instead of this optimal value. So that brings another layer of difficulty.
Right, but that's a very interesting problem. I think that's a very important problem class to look at.
Yeah,
And maybe
yeah,
same ideas can apply.
yeah. Yeah, I fully agree. Actually, previously I have thought about that class of problems, but I haven't got a good enough idea on how to do the decomposition for that problem. Yeah.
Because it also has an application if you have like 3 stages, but you have like not expected value, you have coherent risk measures.
Mm-hmm.
You can sort of transform it into this form, because you get all these kind of consistency issues, which Professor Zelinsky has looked at very carefully, but that you can get a situation where you can kind of merge the first 2 stages into something tractable, but then the 3rd stage is like one of these bi-level stochastic things.
Okay, I see. I will definitely look at those kind of bi-level problems as the next step because this is much easier, I feel, than the bi-level problems.
Yeah.
Thank you very much. Are there other questions? I will have a short question, Ying. So at some point, so you have this difference of convex decomposition. And for the concave part, you use kind of linearization just by using a subgradient.
Yes.
So how easy can one calculate the subgradient of that not very simple function?
That's a great question, but we can always. So I guess you mean this problem,
yes,
right?
I mean, yes.
But the good thing is that for these problems, then in terms of z, we want to compute the subgradient, but we can always use the Danskin theorem, something like that. You compute an optimal solution for this one, but then you compute the subgradient of the joint function, but just the partial subgradient in terms of z. But you asked a very good question, because if this function itself is a optimization problem, minimization problem, but because this is a minimization problem, and if we have a negative sign before it, then this is means that it is you put a negative sign, it is a maximization problem. Then you can merge that maximization with this soup.
Okay.
So that actually for this problem, we lift the dimension from, for example, the pure second stage problem, that space, to join the dimension of this problem. In order to get a subgradient, it will be the dimension of the first stage plus 1 second stage problem. So that is the joint maximization problem. And then that reduced to a value function. And you can, and the Shapiro, they have, or Rockefeller, they have this kind of analysis on the subgradient of that.
So you calculate the differential of value functions, for which there are some formulas. Okay, they are not always exact formulas, but under some, I mean, there is a theory. I mean, there is something. I agree.
Yeah, exactly. Yes. And Shapio's book, he has provided bonus. They have provided.
Of course, then you have a problem with the integral. If your distribution is continuous, it's not a finite sum, then you have a problem of subdifferentiating an integral of non-convex functions. It is highly non-trivial, I would say, and requires a lot of technicalities.
But so that is the reason why when we have continuous distribution, we consider the sampling. We want to avoid that issue. So we just sample some data each time and then reduce it to the fixed scenarios and then redo the sampling, and we add samples and then do it. So, or in other words, this problem is always in the finite dimensional space. Yeah, to avoid dealing with the integral.
Very good. So, thank you very much. Let us stop here. It was a great talk. We had a great discussion. So, we will post the video and the slides on our website and also on our YouTube channel. And I just want to wish you a great week. So next speaker will be Pontus Gislason from University of Lund. So have a great time. Thank you very much. See you next Monday.
Thank
Thank
you,
you.
Radu. Thank you,
Bye-bye.
everyone.
Bye-bye.
Bye.